Welcome back to the course on fluorescence spectroscopy. This is a continuation of the mini series of lectures on fluorescence sensing, which we divided it up into smaller parts, otherwise it just gets too long and I don't think anyone would listen to it. Today we're going to discuss electrolytes in blood. Is going to be our main topic. So determining ion concentrations really is an essential component of research in healthcare. In cell cultures, you're looking at the physiology of the cells and the response to stimuli, so you naturally will want to look at the ion concentrations, oftentimes calcium. In patients, the blood electrolytes reveal something about the health status of the patients, and even can be used to diagnose problems with specific organs. A wide range of pKa values are needed for all these cation sensors because the ion concentrations are different in cells and serum. And just to give you an example of the usefulness, elderly patients also often have an electrolyte imbalance, and the electrolyte balance causes some to fall, and there's a remarkably high fatality rate for elderly patients falling. I guess I look at those things now that I'm getting a little older, never kind of read that stuff before. So they are used to diagnose, as I said, dehydration and organ-specific conditions. Point-of-care sensor could save a lot of time because the physician would know right away whether to start giving the patient an infusion of some electrolyte or combination of ions to balance their electrolytes. And the ions we're going to discuss today are pH, sodium, potassium, and calcium. I'm going to give you a somewhat pessimistic overall conclusion for cation probes. Most of the probes are designed for intracellular use. The ion concentrations are different in blood serum, so many of the probes are not useful in blood serum, and clinical labs typically do not use fluorescence, but rather they use ion selective electrodes to do their measurements. So we won't be focusing too much on clinical considerations. Okay, let's start with the ions. Many pH ions have been reported. That's the easiest ion to detect. Looking at the literature, you'll find a wide range of pKa value, a wide range of wavelengths, wide range of lifetimes. So it can be relatively easy to select a pH probe, but there are some things that should be considered. First, I'm going to start with fluorescein. I never liked fluorescein as a pH sensor, but it's been used quite a bit. Basically, there's a whole variety of cations that are possible, but these two are possibly, they are fluorescent, but they have different intensities. So the pH solution controls the amounts of both species. And this can be used as a wavelength radiometric probe, and it works. For some reason, I've never liked it. But if you excite the fluorescein at 450 and 495, you get a certain ratio between those intensities, which you see the intensity ratio of 495 to 450 goes up with pH. The same thing in this graph here. So many people use fluorescein. Its pKa is actually a little too low for intracellular use, and there's another fluorescein-like molecules. I remember it's called something like BTCE, which has a higher pKa, closer to 7.5, which is more useful in cells. Another widely used pH sensor, and I'll never understand why, is HBTS. HBTS just shows a remarkable shift with pH. So if you shift the pH from up, let's see, 6 to 13 here, the emission spectrum just shifts dramatically. This is not an absorption, this is the absorption spectrum and how it shifts. The reason, unfortunately, the reason that it is pH dependent, of course, if you're looking at this wavelength for 450 or 500, you're going to see the intensity increasing with pH. The reason I think this is unreliable as a pH sensor is because it depends on an excited state reaction. The pKa drops enormously when it's in the excited state. So the moment it's excited, it begins the process of losing this proton, and it begins the process of shifting to the longer wavelength emission. And as a result, the pKa of this, you really can't say what the pKa is because it's going to be different in the same pH solution with two different concentrations of bases, because the acetate, which is the base, there'd be more of it in the one solution than the other, so the apparent pKa would change. But nonetheless, it is in some cases, a useful pH indicator. These are the pH indicators that I really like. In fact, I think they're exceptional. First of all, they're a one-part sensor, and there's no excited state reaction. So the way it is in the ground state is the way it stays. Both states are fluorescent. As you can see here, there's different emission at different pH values. That's important because you couldn't do lifetime-based sensing unless there was sensible emission from both species. And the pKa is in a physiological range, 7.6, 7.7. A number of SNARF and SNAFL derivatives are available. So the SNAFLs have a fluorescein type chromophore. The SNARFs have something that looks a little more like a rhodamine type chromophore. We've used this extensively for pH sensing, and you don't really need to resolve the entire excited state decay. It's a multi-exponential decay because two species are emitting, but you can just look at the phase at one angle or the modulation at one wavelength or the modulation another wavelength, and that alone will determine the pH for you. There's actually a unique advantage to the SNARFL probes, and this is different from many other probes, and that is it has a whole range of different apparent pKa values. I'll say that again. It has a range of different of apparent pKa values, and that is because depending on the emission wavelength, you can collect more of the unprotonated emission or more of the protonated emission. And I apologize, I probably should have put the emission spectra here. But by selecting, this is phase, this one's modulation, by selecting the emission filter you use, just on the long wavelength side, or the wavelength you use by a filter, you can change the pKa, apparent pKa here from 6 to 9, and I guess it's about The same here, 6 to 10. So that can be an enormous value if you're looking at some part of the cell which has a lower or higher pH than another part of the cell. Now the probes for cations, meaning sodium, potassium, and calcium, are almost always two-part probes. There's a fluorescent part and there's a cation binding part. And typically there's some amount of photoinduced electron transfer or some interaction between these parts that causes a spectral shift when in this case, where the proton binds or when a cation binds. And the essence, you can look at this as a classic binding curve. Depending on the concentration of the ion you're looking at, the probe can be 100% in an ion-bound form or 100% in an ion-free form. So how do we build these probes? Well, there's a set of commonly used chelators for this. The chelators for sodium and potassium are azer crown ethers. The larger potassium likes the larger azer crown. The smaller sodium likes the smaller azer crown. And magnesium and calcium also have a different preference for ligand, although I can't really see this in my head in a chemical sense, but they certainly do have different specificities. So let's look, for example, at the sodium and potassium probes. And I have 4 of them here. First, let's look at the sodium probe, SBFI, and potassium probe, PBFI. These were really the first wavelength ratiometric sodium and potassium probes that were reported, and they display changes in emission spectra, which I'll show you in a moment. A very nice probe for sodium is sodium green, which has the same chelator as does SBFI. And then there's frequent interference between sodium and potassium. And that's because the sodium is smaller and it can fit into the potassium azer crown. The vice versa situation is less common. A number of groups have made more specialized chelators. This particular one is more sensitive for potassium. Let's look at the emission spectra of the sodium probes. Sodium probe 1 and then potassium probe, they're both considered to be excitation wavelength radiometric probes. That seems odd at first. The wavelengths we're looking at are 340 and 380. You can see that there will be very different amounts of excitation. Normally they have the same emission spectra independent of the ion concentration. So you can see that's an excitation wavelength ratiometric probe. The same is true for PBFI, but the effect is not as dramatic because at 340 with potassium there's a change in the ion constant, a change in the absorption. But when you excite out at 380, there's very little change in the excitation. So you can use these as sodium and potassium probes. A disadvantage is the short wavelengths cells are often not happy with the short wavelengths. And also there's autofluorescence from the cells at the shorter wavelength, and NADH absorbs, of course. So these are sort of less favored right now. A CD222 you can see is also an excitation wavelength ratiometric probe. The nicest probe is sodium green. because sodium green, it's out in the visible. You excite it, at the 480 nanometer range or so, less damaging to cells, and it shows a large increase in fluorescence. Because both forms are fluorescent, it works well as a lifetime probe also. The problem with all of these are outside of the normal range for blood chemistry, but they're inside the range for intracellular chemistry. And I just did this for convenience, so that on a single slide you could see the probes and the emission spectra for them, and that might make it easier for you to compare which probe shows which type of a wavelength response. All right, how about probes for calcium and magnesium? We'll emphasize calcium. We have Fluor2 and Indo-1 is one of the probes, and they have this chelator, which is the calcium chelator. Calcium green has the same chelator. Magnesium orange, in this case, has this different chelator, which is specific for magnesium. What's the spectral response of these probes? Again, these are the top two, the older ones, Fluor2 and Indo-1. They're the UV ones. They require UV excitation. And once again, they are excitation ratiometric probes. And you can see how the spectra are very calcium dependent. So it's easy to imagine exciting these at 2 wavelengths or exciting into 1 at 2 wavelengths. I hope I have that right. Excuse me if I don't. Looking at the wavelength I have here, it looks like Indo-1 is an emission wavelength ratiometric probe. So I got that one incorrect, but we got to figure it out. Calcium green and magnesium orange, they just give you the same emission spectra all the time. They're both good lifetime probes. And once again, for your convenience, I put them on the same chart for visual comparison, so you can go back and forth between the probe and these spectral properties. Some of these probes are available at multiple wavelengths. Calcium green is great that way because you can buy calcium green, calcium orange. This looks more like a fluorescence. This looks more like a rhodamine, and this looks more like a Texas red. And they have different absorption spectra, and they have different emission spectra. So if you need to change the excitation wavelength or the emission wavelength to detect some other probe, you can switch to one of the other calcium indicators. The calcium green seems to work the best. The calcium orange and crimson don't quite have as good of a response, as you can see by looking from the 0 to the calcium saturated form for calcium green. Got a good tenfold change. For calcium orange and calcium crimson, you have about a threefold change. But for these probes, you can change the wavelength easier, and they all work. And there are also magnesium green and magnesium orange are also available, which I didn't add to this lecture. So what's the status of the cation probes? The status is there's pretty much an ion probe for everything you would want to look at in a cell. pH, sodium, potassium, calcium, magnesium, those are the dominant cations. But I'll emphasize that the pKa range here is different from the pKa range in resting cells or in blood serum. And I have highlighted that on the next slide. So the problem is they're not useful. Most of them are not useful in blood serum. Let's look at sodium and potassium. Sodium in blood serum is about 140 millimolar. Sodium in resting cells is around 4 millimolar. So that's where the FB, Fi, and the sodium probe are centered. So we don't have them for the blood chemistry. A similar thing happens with calcium. The calcium concentration in blood serum is really quite high, about 5 millimolar. The calcium concentration in resting cells is on the order of nanomolar. So all of the calcium probes have their binding constant centered in the nanomolar range, because that's what is needed for the intracellular chemistry. So in terms of selections of probes for your research project, there are simply hundreds of them, and you can go pretty much crazy trying to find the right one. The binding constants for a lot of the probes have been shifted a little bit. As I remember on some of the probes, if you had a nitro group on the ring, you can change the binding constant. And when you look at the literature, you'll find, a whole range of probes for each one. And you really have to decide what your application is before you select the probe. And you probably ought to just select one quickly and see if it works, because there's too many to choose from. And for any non-standard measurements that's not either blood serum or in cells, you really have to look overall what's available and what's available in a AM form if needed. So that is basically it for our discussion of cation probe sensors. Hope you enjoyed the lecture, and I'll talk to you next time. Bye.